Welcome back to our course on complex analysis. In this lecture, we are about to see the concept of fundamental theorem of algebra. This fundamental theorem of algebra tells us that any polynomial of degree bigger than or equals 1 in complex numbers has at least one zero. So by zero, what we mean is a root of a polynomial. Okay, so that is what is written in notation as well. Now let us see how to prove this formally. Right. So first of all, let us take down what the information that is given to us. Given this p of z is a0 plus a1z a2z squared plus etc till an z to the power n. Sorry, there is a typographical an with an not equals 0 and this n may be bigger than or equals 1. Okay, this is the thing. Now let us suppose p of z is not 0 for any value of z. This is the supposition that we are making. It means what? We are trying to go with the contrapositive approach, right? When this is the supposition, then some function f of z, which is 1 upon p of z, is analytic everywhere. Why so? Just because p of z is not equal to 0 for all z. If it is so, what? Every polynomial is an analytic function and the denominator is not becoming 0 for any value of z and the numerator is 1, which is a constant function, that is trivially analytic. The numerator as well as the denominator both are analytic, hence their quotient f of z must be analytic everywhere. So in analytic everywhere, that we can say it as f of z is an entire function. Right? Okay, now let us climb this f of z is bounded. So what is the purpose of showing it as bounded? Because in the previous lecture we have proved in Liouville's theorem that if an entire function is bounded in the entire complex plane, that has to be a constant one, right? So here we have taken a polynomial and we'll have to prove that polynomial has at least one zero, for which we have taken the contra statement, that is it is not 0 for any value of z, with which we have constructed some analytic function which is actually an entire function. If we prove that function is a constant function, that is we are trying to prove f of z is constant by Liouville's theorem. If f of z is constant, then that trivially implies p of z is also constant. A polynomial can never be constant. That is where we will arrive at a contradiction, right? So this is what we are actually going to prove, for which let me write p of z in the form of, let me write it in this form. Now from this, let me write an plus an minus 1 upon z, an minus 2 upon z squared till a2 upon z to the power n minus 1, n minus 2, a1 upon z to the power n minus 1 plus a naught upon z to the power n multiplied with z to the power n. Let us write this way. Okay. Now let us take w to be the quantity a n minus 1 upon z, a n minus 2 upon z squared till a1 upon z to the power n minus 1 plus a naught plus z to the power n. So this quantity, let us take it as w. Therefore, your f of z, sorry, your p of z is an plus w multiplied with z to the power n. That we can verify here. So we have left the first quantity and we have taken everything else to the omega w. So an plus w multiplied with z to the power n is the polynomial function z. So this is what we have. So now observe for large value, for large positive number r, we can find, okay, just a minute. So we are about to find something related to this. So here let me mark this as equation 1. Okay, so we can find the modulus of each quantity, each of the quotients in equation 3 is less than the number absolute of an upon 2n when absolute of z is bigger than r. Okay, here they are not saying this is always the case. What is given is that we are able to identify some suitable large positive number r such that these things are happening. Why is it so? Just because the analyticity everywhere is preserved for, is there for the functions that we have taken. That is why we are able to identify like this. Now okay, from equation 3, what is absolute of w? That is absolute of a n minus 1 upon z plus a n minus 2 upon z squared etc till a2 upon z n minus 2 plus a1 upon z to the power n minus 1 plus a naught upon z to the power n. This is what we have. Okay, so by triangle inequality, generalized triangle inequality, so we have this quantity to be equal to this and this quantity to be equal to this. So if you notice, what we have said here is that all of this quantity is lesser than an absolute of an upon 2n. So all of this quantity, all these quantity are to be replaced with absolute of an upon 2n plus absolute of an upon 2n, absolute of an upon 2n. This is happening for n times. So this quantity is equal to n times of absolute of an upon 2n, that is absolute of an upon 2. Right? So ultimately what we have is absolute of w is smaller than absolute of an upon 2 whenever this is happening only when absolute of z is bigger than r, right? Consequently, absolute of an plus w is bigger than or equals absolute of an minus absolute of w under whole absolute sign, right? So this is okay. We have the negation sign, right? So when you negate it, what you get, which is bigger than absolute of absolute an minus absolute an upon 2, which is equal to absolute of an upon 2. So this is happening whenever absolute of z is bigger than r. Okay, so with the help of this, if we just take this one as equation 2, by equation 2 what we have is absolute of p of z is bigger than or equals absolute of, sorry, not bigger than or equals, actually equals absolute of an plus omega multiplied with absolute of z to the power n. The first quantity is bigger than absolute of an upon 2 and this quantity is bigger than r to the power n, right? So this is happening whenever absolute of z is bigger than r. So let us mark this as equation 3, right? Now let us check the boundedness of f of z. Therefore absolute of f of z is equal to 1 upon absolute of p of z, and this p of z is bigger than or equals this quantity. So when we take the reciprocal, it will turn to be a smaller than or equals quantity. So this is smaller than 2 upon absolute an multiplied with r to the power n whenever absolute of z is bigger than r. So this just concludes f of z is bounded in the region exterior to the disk absolute of z smaller than or equals r. So here what we have done is that we have identified a very large disk of radius r, and outside this disk we have proved the function is bounded. Okay, now it is left to talk about the nature of the function inside this disk, for which what we are going to do is that we observe f is an entire function. Okay, so this property entire function gives us that f is basically analytic. This analyticity will imply differentiability, and this differentiability will imply continuity. Okay, so what f is a continuous function on absolute of z smaller than or equals r, which is a compact set. In simpler terms, we can have it as closed and bounded. Okay, when the closed and boundedness is there for this clearly will give us that f of z is bounded in absolute of z smaller than or equals r. So the image set inside which also it is bounded. That is what we are saying using the compactness of the disk. Okay, so combining these two things together, f of s is a bounded function on entire C. Therefore, by okay, together let us write it together. F of z is a bounded entire function on C. Therefore, by Liouville's theorem, f of z is constant. This eventually tells us that 1 upon f of z, which is nothing but p of z, is constant. But this is a contradiction. Therefore, p of z has at least one zero in C, and this completes the proof. Right? So, this is some, we may have it as a remark or anything you want. Okay? If you are given a polynomial, you can find at least one root. That is what your fundamental theorem of algebra tells you, right? If p of z is p of z is a polynomial of degree n with n bigger than or equals 1, then by fundamental theorem of algebra, we have at least one root or 10 for p of z, say z1. Okay, then your p of z may be written as some z minus z1 multiplied with q of z, where this q of z is a polynomial of degree n minus 1. Okay, we can just apply the same argument shall be applied to q of z. Therefore, p of z is z minus z1 multiplied with z minus z2 and q2 of z. So the repeated application of fundamental theorem of algebra this is going to give us what? So we can just linearly factorize the given polynomial. So P of z would be c times of z minus z1, z minus z2 till z minus zn. Okay, in between there may be repetitions of the zeros, that is of no bother, but still we can write them in linear factors. This is what we are saying. Okay, so here at most n roots is the thing that we can assure. We cannot assure exactly n roots, because just before I told you people that there may be repetitions of roots which are accounted to. But even in this case, if suppose z1 is the thing that is repeating, we just write it as z minus z1 multiplied with z minus z1. Okay, so we account it once, but we write it twice. Okay, at most n roots is the thing that is guaranteed by the fundamental theorem of algebra. Okay, if you see, here we have a lemma. This lemma is used in order to prove what exactly the maximum modulus principle is. This maximum modulus principle can be stated in two ways. One way is given in the theorem and the other way is given as a corollary, right? So this corollary is mostly used in order for problem solving. Now, in order to begin with these things, let us start with this lemma. Okay, let us see what is given in the lemma. Suppose that absolute of f of z is smaller than or equals absolute of f of z naught at each point z in some neighborhood of z naught with epsilon radius. Okay, so that neighborhood has to be taken in such a way that the function z is analytic inside the neighborhood. So when we talk about the analyticity, we of course need some neighborhood in which the differentiability is preserved. Such type of neighborhood is chosen. Then if it is so, okay, here z0 is a fixed point around which you have taken the neighborhood, and the analyticity is present at the particular point as well. If this is so and that condition is satisfied, that is the very important point here. The analyticity and the for analyticity we of course have some neighborhood. These things are naturally there. The extra condition that is imposed here is absolute of f of z is smaller than or equals absolute of z naught, and z naught is some fixed point. Then the claim of the lemma is f of z has a constant value, and that constant value equals f of z naught throughout that neighborhood. This is the lemma. Tells us, let us prove the lemma. So in order to begin with the proof, we assume that, or we just write given f is analytic at z naught, and suppose absolute of f of z is smaller than or equals absolute of f of z naught at each point z in some neighborhood. Absolute of z minus z naught is smaller than epsilon. In some neighborhood it is satisfied. Okay. Next, we let rho be the distance between z1 and z0 for some point z1 other than z0 in the neighborhood. So what exactly happening here is, suppose we have something of this sort and this is our z naught, and let us say so we have some neighborhood of this form. Okay, so for some point z naught with epsilon radius we have found the neighborhood, and inside this neighborhood you will have to identify some point that is z1. Okay, so you can have your z1 to be here and taking this as this distance as rho. So this is what we are doing, right? Next, if c rho denotes the positively oriented circle, absolute of z minus z naught equals rho centered at z naught and passing through z1. So that is, we'll have to consider a circle inside this neighborhood in this direction. Okay, then by Cauchy's integral formula, what we are about to have is f of z naught equals 1 upon 2 pi I integral over 0 f of z upon z minus z naught dz, and we mark this as equation 1. Okay, now let us give some parametric representation. So that parametric representation, the parametric representation for 0. Okay, so absolute of z minus z naught is given to be rho, right? So this tells us z minus z naught is rho e to the power iota times of theta, with theta lying between 0 and 2 pi. So with which one can write z equals z naught plus rho e power I theta with 0 less than or equals theta less than or equals 2 pi. Okay, so with this parametric representation, with this parametric representation, we have f of z naught equals 1 upon 2 pi I, and the interval value becomes what? 0 to 2 pi, and in the place of f of z we have f of z naught plus rho e per iota times of theta, and the denominator z minus z naught is rho e per iota times of theta, and the derivative of z is what? It is rho iota times of e power iota times of theta d theta. Okay, this gets cancelled and this iota gets cancelled, and we are left with f of z naught equals 1 upon 2 pi integral 0 to 2 pi f of z naught plus rho e power iota times of theta d theta. This is what we have, right? And we mark this as equation 2, and this equation 2 has something to say about us. something to tell us. What is that? So by equation 2 we observe when a function is analytic within and on a given circle, its value at the center is the arithmetic mean of its value on the circle. What is the arithmetic mean of continuous function? It is integral over the given limit of that function is going to give us the uh, arithmetic mean of that function multiplied with its length. So in order to get the arithmetic mean, we just divide that integral quantity by the length of the interval, then we get the arithmetic mean. So here the arithmetic mean of the function f of z is equal to the f of z naught, which is the center of a circle, right? So that is what is said here. This result is called Gauss mean value theorem. Okay, this is some other result which is not related to this maximum modulus principle, but when we proceed with the proof of a maximum modulus principle, we observe this result is happening to be true, right? So now let us continue our discussion about this lemma. Okay, so from equation 2 we get absolute of f of z naught is equal to absolute of 1 upon 2 pi integral 0 to 2 pi f of z naught plus rho e power iota times of theta d theta, and this is smaller than or equals 1 upon 2 pi integral 0 to 2 pi absolute of f of z naught plus rho e power iota times of theta d theta. Okay, we mark this as equation 3. It is given that absolute of f of z is smaller than or equals absolute of f of z naught. Okay, so this it tells us absolute of f of z naught plus rho e power iota times of theta is smaller than or equals absolute of f of z naught, and this is true for theta varying between 0 to 2 pi. Let me mark this as equation 4, right? So with which what we can say, if these two functions satisfy this inequality, then integral 0 to 2 pi absolute of f of z naught plus rho e power iota times of theta d theta is smaller than or equals absolute of 0 to 2 pi integral 0 to 2 pi absolute of f of z naught multiplied with d naught, and this gives me simply 2 pi times of absolute of f of z naught. So with which I can write absolute of f of z naught is bigger than or equals 1 upon 2 pi times of integral 0 to 2 pi absolute of f of z naught plus rho e power iota times of theta d theta. And let me mark this as equation 5. Now from equation 4 and 5, so what is equation 4? That is absolute of f of z naught is smaller than or equals 1 upon 2 pi times of integral 0 to 2 pi absolute of f naught plus rho e power iota times of theta d theta. And equation 5 is, sorry, that is not equation 4, that is equation 3. So using equation 3 and 4, we can come back, we can just write absolute of f of z naught is equal to 1 upon 2 pi times of integral 0 to 2 pi absolute of f of z naught plus rho e power iota times of theta d theta. Okay, so with which, what can I write? I can just bring this 2 pi quantity to this side is equal to 0 to 2 pi absolute of f of z naught plus rho e power iota times of theta d theta. And here what can I do? This shall be written as integral 0 to 2 pi absolute of f of z naught d theta equals integral 0 to 2 pi absolute of f of z naught plus rho e power iota times of theta d theta. So when I bring everything into one side, what I am going to get is integral 0 to 2 pi absolute of f of z naught minus absolute of f of z naught plus rho e power iota times of theta d theta. Okay, so here the terms that we have inside this integral are all continuous, right? So now using equation 4, one can verify that this quantity absolute of f of z quantity is always a non-negative quantity. So when we have an absolute of this quantity is a non-negative quantity, when we integrate some non-negative quantity, we are getting that to be equal to 0. This can happen only when the integrand itself is 0. Only when this is 0, that can happen. So this trivially gives us what? Your absolute of f of z naught plus rho e power iota times of theta is equal to absolute of f of z naught, right? So which means your absolute of f of z is equal to absolute of f of z naught for all z in the neighborhood. So this is happening to be true, right? So sorry, not for all z in the neighborhood, for all z in the circle, absolute of z minus z naught equals rho. Okay, now we'll have to extend the result to the neighborhood. Okay, so now let us proceed with the fact that since z1 is any point in the deleted neighborhood, in the deleted neighborhood 0 smaller than absolute of z minus z naught smaller than epsilon, we see the condition absolute of f of z is equal to absolute of z naught is satisfied by all the points z lying on any circle absolute of z minus z naught equals rho, where this rho lie between 0 and epsilon. Okay, for any circle it is happening to be true. Initially you have chosen like, suppose here you have chosen this to be your rho is specified in the diagram itself. Now if I choose my rho to be some other, like if I choose my point here and I take this distance to be my radius, and with which I can form a bigger circle, even I can form some smaller circles, it is up to me, right? So whatever may be the point that I choose, for which I am taking a neighborhood, inside which I am able to choose my circle as the way I want. I can choose any point in the neighborhood, and with respect to that point I can find some radius, and with that radius I am forming a circle, and I am talking all these things. So with that ideology, we are saying that whatever may be the point that I choose, and whatever may be the radius that I choose, actually based on the point only we are choosing the radius, for all possible radius this is happening to be true, right? So with which what we can conclude is that absolute of f of c equals absolute of f of c naught everywhere in the neighborhood. Everywhere in the neighborhood, absolute of z minus z naught less than epsilon, right? So we just proved the absolute quantity is equal, but we know that when the modulus of an analytic function is constant in a domain, the function itself constant in the domain. So if you just notice the wordings that I have written, I just said that when the modulus of an analytic function is constant in a domain, that may be on any domain, the function itself is constant in that domain. Okay, which means there initially you have the flexibility of choosing any domain that you want. Okay, once you have chosen the domain, we are talking about that particular domain. That is why we have the article add domain there and the domain there. Okay, so with which we just conclude f of z equals f of z naught for each point z in the neighborhood. And this completes the proof of the lemma. Thank you.